So from that simple preview that we have done, now let's talk about the diagonal relationship. Like I told you, you can mute. It's okay, you can mute. Like I told you, the periodic properties must be part of you. Okay? Because they are the ones that make inorganic chemistry. And we finished all the periodic properties. Okay, we finished most of them, and we are remaining with just diagonal relationship. And it just like the other periodic properties, this one is also easy. Actually, very easy, if not the easiest. Because I'm sure all of you here, you do make relationships, you do have relationships. Okay? However, your relationships are not diagonal. Maybe they are horizontal, maybe, I don't know. But all of you have relationships, and the relationships are diagonal. So if you know that, then the definition becomes easy. Okay? Diagonal, it is in P7, you are told that this is a diagonal. And also this is another diagonal. So if you have maybe your two elements, one is here, okay? Oh, your two elements are like this. You have A, you have B, you have C, you have D, you have E, you have F. Where A resembles where A resembles D, okay? In their properties, you can see A and D are diagonal. Even B and F, they are also diagonal, as you can see. So if these diagonal neighbors, if these diagonal neighbors share some things in common, okay, then we shall call this a diagonal relationship. Let me first check. Since so from that simple illustration, therefore, how can you define diagonal relationship? It is simply the similarity in both chemical and physical properties between members in a periodic table. And which members? Members of period 2 of the periodic table to their diagonal members in period 3, okay, of the adjacent groups. So if you can define it in that way, actually, I don't need to cram this. I don't need to cram the definition. Just know what diagonal relationship is. You know what it is. The rest becomes easy. They are members in period 2 having similar chemical and physical properties to members of period 3, but of the adjacent groups. Okay? So if this is my period 2, okay, and this is my period 3, so a member in period 2 has similarity in chemical and physical properties with a member in period 3, but with a diagonal member in period 3, but of the adjacent groups, this group and this group. So the member automatically becomes this, or the relationship automatically becomes for these two elements. And within a periodic table, we have elements that do show diagonal relationship. And that's lithium and magnesium, then beryllium and aluminium, then silicon and boron. These are the members that really show diagonal relationship within a periodic table. So you can see this is lithium, and lithium is in group 1, but it has some similarities in chemical reactions with magnesium. They are reactions where both undergo the same. In other words, one deviates from other members in that particular group. You see beryllium, it is in group 2, but it has reactions that are similar to aluminium, which is in period 3. Boron is in period 2 and in group 3, but it has reactions that are similar to silicon, which is in period 3 and group 4. So this similarity in both the physical and the chemical properties between members of period 2 to their diagonal neighbors of period 3 in the adjacent group or groups is what we refer to as diagonal relationship. So you can still have a look on the periodic table. So these two, then this and these two, they also show some similarity. And finally, these ones, they also show some similarity. And that similarity is what we refer to as diagonal relationship. Is that okay? So that is basically what diagonal relationship is about. That similarity, okay, in both the physical and the chemical properties among elements of diagonal neighbors of period 2 and period 3 is what we call diagonal relationship. Now, you should be asking yourself why? Why? Like why do these elements show diagonal relationship? What is the science behind diagonal relationship? Why should they be the same? Why should lithium and magnesium? Why should lithium, okay, and magnesium, lithium is in group 1, magnesium is in group 2, but they have some similarity in the chemical properties. Beryllium and aluminium, Al. Beryllium is in group 2 and aluminium is in group 3, but the two show some similarity in the physical and the chemical properties, but mostly chemical properties, not physical. Okay? Why do they show some similarity? Okay? So if you can answer that, if you understand this concept, then you'll be good to go as far as diagonal relationship is concerned. So let's see. Now, from what we've been studying, from those periodic properties that we've been studying, we have been seeing that if a given property, for instance, okay, charge density, if it increases across the period, the property decreases down the group. Are you seeing? If a property, may be electronegativity, increases across the period, it decreases down the group. If a property, any property, maybe ionization energy, if it increases down the group, then it decreases. So if it increases across the period, then it decreases down the group. Are we together? Do you still recall that? Do you still remember that? Yes, now that is the same principle. that is working here. So if a property increases across the period and a property decreases down the group, then diagonally, okay, diagonally, the increase here is counteracted by the decrease here, such that if you try to move diagonally, almost they are the same. These two elements, they will almost be the same. That's why these diagonal neighbors, the diagonal relationship elements will show similarity in the chemical properties, okay, due to similar polarizing power, okay. The polarizing power is the same. Not the same, sorry. The polarizing power is not the same, but the values are close to each other. The values are almost the same, okay. So we say they have similar polarizing power or similar charge density. As if that's not enough, they also have similar electronegativities, because we have said across the period electronegativity increases, but down the group electronegativity decreases. So diagonally, it's all going to be the same. The electronegativity is going to be the same for these diagonal members, and so they will tend to have similarity in the chemical properties. Then similar electropositivity, the same. If electropositivity increases down the group and decreases across the period, diagonally it cancels out. Those two effects cancel out, such that elements, maybe for example lithium, okay, and magnesium, they almost have similar electropositivity. Which other factor? You have similar electrode potentials. Yes, we shall see this. But electrode potential, it is the reduction potential or the electromotive force between two galvanic cells, two cells. Okay? So it is that reduction potential, the reduction ability of an element. Okay? Let me summarize it as that. So if electrode potential increases across the period and decreases down the group, then it means diagonally it will cancel out, and diagonal members will almost have the same. Is that okay? Yes, so you can drop it. So since there are no questions, then let's proceed. So basically that is diagonal relationship. Members in group 2, sorry, in period 2, showing some similarity with members in period 3, or with diagonal neighbors in period 3, but of the adjacent groups. Then that one becomes diagonal relationship. And why the similarity? We have seen that across the period, a given parameter, a given property, periodic property, is going to increase. Down the group, it is going to decrease. So if you move diagonally, then the effect is going to be cancelled out. So let's check on some reactions where lithium resembles magnesium, or where magnesium resembles lithium. Okay? And you need to know these reactions one by one with their equations. Okay? Yes. Now for group 1 elements, when they react with oxygen, they burn in oxygen to form oxides, to form peroxides and superoxides. That is group 1 elements. But now, for lithium, now it deviates from the norm. For it burns in excess air to produce normal oxides. And why does it do so? It is because lithium has a high charge. a high charge density. So the charge density being high, it can accommodate the highly electronegative oxygen atom. Okay? Now that is the lithium. But for other elements, the sodium, mhm, the sodium, which other elements of group 1? The potassium, then can we guess? The cesium, and finally the rubidium. So these other elements, for them they form peroxides for the case of sodium, but potassium, cesium, and rubidium, for these ones they do form superoxides. Why? Because they have low charge densities. Okay? Yes. And for group 2, all group 2 elements combine with oxygen to form normal oxides. So now, do you see that lithium is trying to resemble the group 2 elements? Yes, if you can observe that, then you are good to go. Then they do combine with nitrogen to form nitrides. Both lithium and nitrogen and magnesium.
Excuse me, sir.
Yes.
Why are they called normal oxides? Should I think that they are abnormal oxides?
Why are they called normoxides? Anyway, they are now they are called normoxides because, let me first take away this. Because any element normally they do combine with exchange of oxidation state. Where lithium has one and oxygen has two. So they will exchange the oxidation states, their valencies, and this one comes here and this one goes there. And you form lithium 2, oxygen 1. Okay? So now this is a normal oxide. This is what is expected. But for peroxides, you form this. Can you imagine? Sodium with a 2 and oxygen with a 2. Now what is this? Hmm? What is that? What is the valence of sodium in this case? Now for superoxides, you form this KO2. Can you imagine? Have you ever seen this anywhere in your life? So now these are abnormal. They are not as expected. Okay? They are not as expected. So they are not normal oxides. So I hope this one is explained now. So they do combine with nitrogen to form nitrides. Okay? And for example, you can check on this lithium plus nitrogen, you form lithium nitride. And when you try to balance, nitrogen has a valence of 3, lithium has a valence of 1, then that's what the compound that is formed. Then with magnesium, magnesium has a valence of 2, then nitrogen has a valence of 3, and so that is the compound that is going to be formed. Magnesium. So this is the compound that is going to be formed. So, but for all group 1 elements, no other member that can burn.
Excuse me, sir.
Yes,
Where are you writing? Are you writing on this slide? I'm not seeing something. I'm not seeing anything being written there.
sure. If I do
Yes,
this, you can't see anything. Uh-huh.
I'm not. I've just, I've just seen the pen you're using, but the writings you are doing are not there.
You mean if I write this, you can't see?
I'm not seeing it.
Oh, Tim, what is this?
First repeat.
What is this?
Sodium peroxide.
But for you can now see. How come Edwin can't see? Hmm? Eh, mhm. What is this, Otim? What is this I'm writing?
Like potassium carbonate.
Potassium carbonate. You can. Eh, Edwin, how come you are not seeing what I'm writing? Edwin?
Yes,
Uh-huh. You can't see anything? Anything in red?
they have just appeared, but when you were explaining, they were not there.
Maybe it's a slow connection. It could be. It could be a slow connection. But they are there. They are there. Okay? Yeah, so like I said, for lithium and magnesium, they do combine with nitrogen to form their nitrides. And this is unique. Okay? This is specific to magnesium, okay, and the lithium. The rest of the group members don't. Okay? The rest don't. So why these ones? Why do they have then similar reactions? It is because of diagonal relationship. And which explanation can you give? The above slide. That they have similar polarizing power, similar electronegativity, similar charge density, which is the same as polarizing power, similar electropositivity, similar electrode potential. Not same. If you say same means if it is 20, then they will all have 20, which is not the case. But you may find when one is 20, then another one is either 19 or 20.5. So they are similar. Okay? And so because of this similarity in those periodic properties, then it results into having similar chemical reactions. Is that okay? Yes. And how they combine with carbon to form carbides? Yes. They do have ability to form carbides. And there's other group 1 members and other group 2 members. Anyway, for other group 2 members, for them they can. For them they can form carbides. But for group 1, okay, no other group 1 element can form a carbide. Is that okay? Yes. And so this is a trait, in quotes. This is a reaction where lithium resembles magnesium. Is it good? Is it explained? And you need to know, by the way, how to write these chemical reactions.
Teacher,
Yes,
what if I don't want to write the ion of carbon like that?
it is okay. Just write magnesium carbide. But they are two. Anyway, just write magnesium carbide. Okay? This is one. Just write this. It is okay. Okay?
For the ionic equation, it strictly should be like that.
And nobody is going to ask you for ionic equation. Nobody is going to ask you for it. This one, I was just trying to stretch the bond to show you a carbide. For example, for the lithium carbide, you have a minus here, and then and then lithium, and then a minus here, and then lithium. So it's what I was trying to show you, but it's okay. You can write lithium carbide. Okay, it is okay.
Teacher,
Yes,
a carbide is a radical.
not a radical.
It's a
It's a derivative of alkyne. So
yeah.
a triple bond, instead of hydrogen here, you put the metal, the highly electropositive metal.
So it can't
It can't.
exist on its own.
And no,
Exist on its own, a carbide.
you can't have
So
carbide.
it's a radical.
No, radicals, they are formed by having unpaired electrons. Okay? Maybe when
Yeah.
a covalent bond undergoes a homolytic fission, okay? One takes
You
one
share.
electron and another one takes another one electron. And so what you form radicals. Why radicals? Because they do have unpaired electrons. Not so?
Yeah.
But this is not a radical because you can see they are ions, they are charges. It received 2 electrons from the hydrogen. Even this one also received 2 electrons from the hydrogen. So when they combine with these high electropositive metals, then you form the carbides.
Okay.
Yeah. I hope it is okay now.
Yeah.
So other than lithium, then no other element in group 1 can combine to form a carbide. So we should really give a standing ovation to lithium, okay? Because for it is unique from other group 1 elements. Is it okay? Yes. Sorry for that. So this one is the same as they are the same. They both form normoxides, and somebody asked why normoxides? Because that's what is expected. Okay? Then that was lithium and magnesium. And you need to know, because this question also it appears. Actually, after here you go to a classroom, there are questions concerning diagonal relationship. There are questions there. You go and do them. Go and do them. Okay? To gain more knowledge as far as diagonal relationship is concerned. You need to know, you need to explain why they show diagonal relationship and also some examples. Okay? Some examples that these elements have that show, or that they have in common, or that they undergo in common, that they have the similar reactions. You should know them, and you should know how to write the equations, well balanced equation. By the way, as if there's something I haven't told you. In organic chemistry, it is about equations. Okay? Equations. If you write a correct equation, you earn yourself half a mark. If you balance the equation correctly, you earn yourself half a mark. And if you write states I mean solids, liquid, gas, you also earn yourself half a mark. So the whole equation, you're going to earn 1.5. And this 1.5, you think it's easy to get 1? You think it's easy to get it? So within organic, understand the periodic properties, and then after understanding these periodic properties, then understand equations. Equations. That will be your magic bullet. If you know how to write the equations, then you can never fail any inorganic question. And always inorganic question will always be easy for you. Okay? And it's easy. That is if you're prepared for it. So now with beryllium and aluminium, they are all passive. They are all rendered passive with conc nitric acid. For both beryllium and aluminium, both don't react with conc nitric acid. But however, other group members in group 2, they all react with nitric acid. Both are amphoteric. Both beryllium and aluminium, they are all amphoteric. This is aluminium, this is beryllium, let me not assume. They are all amphoteric in that they can all react with acids, and at the same time they can react with bases. No other member in group 2 can do that. No other member, maybe in group 3. Now in group 3, which other member? Boron? I don't think. Anyway, we shall study boron. So they are amphoteric. They can react with both acids and bases. So with bases such as sodium hydroxide, hydrogen gas is involved. They can react with it. Okay? That's beryllium plus the base, and the reaction occurs in presence of water. You form that tetrahydroxo beryllium 2 ions, and then the hydrogen gas. You need to know how to write this equation. Okay? Yes. Also with aluminium reacting with the sodium hydroxide, okay, in presence of water, you forming a complex which is tetrahydroxo aluminate 3 ions, and the hydrogen gas is going to be evolved. So for both elements in group 2, no other element in group 2 can react with both the sodium hydroxide and both acid. However, when they reacted with acids, they will form a salt, and hydrogen gas is going to be evolved. Okay? Yes. Hydrogen gas is going to be evolved. I hope it is okay now. Any question for me? Because you've been asking, which is good. Any question for me? No question. Another factor is the oxides and hydroxides of beryllium are amphoteric. Now this was for these two. They are metal atoms. They can react with both acids and bases. But still, the oxides that are formed, they are oxides. They are also amphoteric in that they can react with both acids and bases, unlike other elements, okay, in their groups. So you can write the equations. Now, because of high charge density, okay, and a high polarization power, both the chlorides of lithium and aluminium, they do dimerize. Where is my pointer? It has disappeared. They do dimerize. What does that mean? They do exist as dimers in vapor form. Okay? That they have a low boiling point. Okay? That when you hit them, then they can easily sublime to form dimers. And why is that happening? Because instead of forming a normal ionic bond, beryllium, which is a metal, reacting with chlorine, which is a non-metal. So this bond, it is assumed to be ionic bond. Even with aluminium, you can see aluminium with chlorine. This bond is also assumed to be ionic bond. That, like I said, it's an assumption. It is an assumption. But truth of the matter is, these bonds are not ionic. They are not pure ionic, but they are more of covalent bonds. Why? Because these ions, these metal ions, the beryllium and the aluminium, they do have a high polarization power. Okay? That they will highly polarize the aluminium chloride bond. This ALC, this bond, and the BE, the beryllium chloride bond. And if you polarize it, then the bond ceases from being an ionic bond to become more of a covalent bond. Okay? To become more of a covalent bond. And as a result, you decrease the boiling point, the melting point, so that this one can now easily sublime to form diamonds. Okay? And when you dissolve, since to show that these bonds are covalent, when you try to dissolve them in organic solvents, the beryllium chloride and aluminium chloride, they will dissolve with ease. But these are ionic bonds. A bond between a metal and a non-metal, metal and a non-metal, they are ionic bonds. Okay? So ionic bonds, the bond is assumed to be polar, so it should dissolve in polar solvent. It should dissolve in water. But see what is happening? The bond is dissolving where? Sorry, the salt is dissolving where? In organic solvents. So which becomes confusing. Okay? Which becomes confusing. And when you try to dissolve it in water, yes, it will dissolve, but finally it will undergo hydrolysis, where it will react with the water molecule to alter the pH. Okay? To change the pH of the resultant solution. So instead of the solution formed to be a neutral solution, now the solution that is formed is going to be slightly acidic. Why is it acidic? Because it has undergone hydrolysis to produce hydrogen ions, which will alter the pH. And we shall write equations, however, not now. Then beryllium carbide and aluminium carbide, they are carbides. They do dissolve in water to liberate methane gas. Okay? And this is unique to beryllium and aluminium carbide. For example, group 2, for example, calcium, it evolves ethane. But now this one, it is evolving methane gas. Okay? It evolves methane gas, which is also some unique feature, some unique property. Okay? Between the beryllium and the aluminium carbide. Is it okay? Yes. So let's talk about boron and silicon. Maybe if there is questions, if we have some questions, then it's okay, we can attend to the questions. Okay, so since there are no questions, then we can proceed. Now for boron and silicon, they also show some similarity. Okay? In their physical and in their chemical properties. Number one, boron being in group 2. Sorry, group 3. It is supposed to be a metal. Because group 3 elements, they are metals. Why? Because they have 3 electrons in the outermost shell. So they are regarded as metals. However, now for boron, the reverse is true. For boron, for it, it's a non-metal. Okay, it's a non-metal, and silicon too is a non-metal. Okay, and they do have similar properties. And why boron and silicon? Because we saw they are diagonal. Boron will be in group 3 somewhere here, and silicon in group 4 somewhere here. So they do have some reactions that are common to all. Okay, whereby for example, let's check on those reactions. Number one, they all do form covalent compounds. Why? Because they are metals. They are oxides, the boron oxide and the silicon 4 oxide. They are strongly acidic. What does that mean? The oxides can dissolve in water to produce an acidic solution. Those are the acidic oxides. And which acidic solution? You have the oxyacids, the the boric acid, and the silicic acid. When the oxides are dissolved in water. And when these acids are reacted with aqueous alkalis, you produce a borate and a silicate, depending or respectively. Now they all do form covalent chlorides. This one is assumed to be a metal because it is in group 2. But see, it is forming covalent chlorides that cannot dissolve in water even. Okay? But rather will dissolve in organic solvent. And their chlorides all undergo hydrolysis to produce. Now, are we going to produce an acidic solution or basic solution? So you can find out. But all their chlorides for both boron and silicon, they all undergo hydrolysis. Then they all form borides, e.g. magnesium boride. Now you see, this one is a metal. Okay, you see, it is a metal, but instead it is combining with other metals. Can you imagine? Because it is in group 3, and so it has an oxidation state of +3. So it is assumed to be a metal, but see, a metal is combining with other metals. Okay, so it becomes confusing. But now other group 3 elements. Talk about aluminium. Aluminium cannot combine with any metal. They are all electropositive metals. You combine aluminium with magnesium, what will you get? I don't even know. Then silicides, where magnesium reacts with silicon to form magnesium silicide. But this one occurs when they are heated. Okay? Yes. And that's how we finish the periodic properties. And I'm going to stop from here today.